Brilliant. Thank you very much, Annie. So I'd like to kick off by welcoming everybody to this session. I'm Kirstine, Principal Fellow for Data Sciences at the Met Office in the UK. And I'm guiding us through this session with my colleague, Dr. Chris Slocum from NOAA, who today is representing the organising committee for the conference. Before we start, I'd like to remind everyone that we are committed to providing participants of the workshop a safe, productive, inclusive and welcoming environment for everyone. So naturally, harassment, intimidation and discrimination of any kind will not be tolerated. And if you have any concerns or any positive feedback, you never know, feel free to drop us an email. So before we start, a little bit about the session. This is, just to check everyone's come to the right session, this is Communities of Practice and Workforce Development. There are two characteristics that I should point out early on about this session. Number one, it's very exciting and very interesting. We've got some really interesting and great speakers lined up for you, so I have high hopes for this session. It is jam-packed with interesting stuff. There were lots of abstracts submitted for this session, too many for us to accommodate. So we have chosen creme de la creme. Hopefully you will enjoy this journey as much as we did putting it together. The second characteristic of this session is that it's going to be pretty pacey. We've just got 90 minutes. We've got a 20-minute talk from Stephen Haddad from the Met Office, and then 10-minute talks from a series of other speakers. But it's going to be a fair canter to get through this exciting material. So cling on, hold on tight. It's going to be fantastic. It's going to be worth it, but it is going to be quite a lot of material to take in. So to maximize the value of this session, can we encourage you to do two things? First of all, we've allowed 2-minute transitions between the talks, and I'm sure the speakers are all going to keep to time. So you've got your 2 minutes, and in those 2 minutes, can I encourage you to reflect upon the talks, to think about how they might apply to the organisations that you work in or your day job, and can I ask you to think about any questions you might have for the speakers? Second thing I'd like to ask you to do is, when you've thought of the questions, please could you pop them in the Slack channel? So we've got a Slack channel, I think it's channel 5, I think. If you could pop your questions in there. Chris has very kindly volunteered to have a look at the questions and identify some that we can talk about at the end of the session during the Q&A session. But most importantly, if you put your questions and comments into the Slack channel, that's going to keep this conversation going. The Slack channel stays open beyond the end of this session. So this is a way for us to continue the conversation, so to keep this going. I think there's going to be more conversations and more material, more value that you're going to want to extract from this session than we can possibly do in an hour and a half. And the Slack channel is the way for us to achieve that. So I said it was going to be pretty pacey. I've already taken 4 of your precious minutes. So I'm now going to hand over to my colleague at the UK Met Office, Stephen Haddad, to talk about embedding data science in the Met Office through a community of practice. Stephen, over to you.
Excellent. Hopefully you can see my slides.
Yes.
Super. Right. Well, let us begin then. Hello, my name is Stephen Haddad. I'm a scientific software engineer at the informatics lab at the Met Office, where I work in machine learning and data engineering. But over the last year and a half, I've also been involved in organizing our data science community of practice at the Met Office. And that's the focus of my talk today, talking about how we not just organize a good community of practice, but how that aligns with the goals of our organization and embedding data science in the Met Office in the long term. So let's start with having a look at the background to data science at the Met Office. So the Met Office, like many weather and climate organizations, is a historically data-driven organization. Back when it was founded in the 19th century by Admiral Fitzroy, the first thing they did was start gathering data, measurements, and on the right-hand side here in the image, you see one of the first barometers that was sent out to a fishing community in Scotland to measure the pressure to be used as data for forecasting the weather. Well, ever since then, data volumes have only grown through more observations, including satellite and radar, high resolution weather and climate model runs, ensembles of those runs. Data has continued to grow basically faster than we can make use of and exploit that data. And although we've long used many techniques like statistics to process and analyze that data that are related to machine learning, data science and machine learning, for me, one key aspect is it allows us to scale up our analysis to meet the challenge of the huge volumes of data, which is both a threat and opportunity because many organizations now have the opportunity to do that. So we also need to be doing it. But it's an opportunity for the Met Office to really get on top of making the best use of all the data we have. And one potential way of doing that is a community of practice. Why in particular, though, a community of practice? I think there's three key things about a community of practice that make it useful. Firstly is learning and development. So for any particular field, in this case, data science, it forms a sort of entry point for people who are looking to get into that field and learn more about it. That's a good starting point. But at the other end, at the cutting edge, courses only go so far in terms of learning. It's all about learning from peers and what's happening in projects done by your peers. And it's also a good opportunity to develop your communication skills around the field, practicing conference talks and so on. The other key thing about communities of practice are that they provide links between teams. When communities of practice or guilds were pioneered at Spotify, which is one of the early pioneers in the current wave of communities of practice, it was all about people doing the same thing in different teams who didn't otherwise talk to each other. So they allow people to talk to each other and develop best practices around whatever task they're doing, in this case, data science and machine learning. And in general, it's a good support network to discover people with related skills and activities. When you're stuck on a problem, it's an informal support mechanism and place to sound off ideas. So that's the idea of a community of practice generally. So bringing those two things together, the Met Office data science journey and the community of practice, what's the background on our current community of practice? Well, we had a community previously that was called the Machine Learning Forum. That was more a sort of place to talk about how we might apply machine learning to weather and climate, which wasn't really being actively applied in projects at the time. And so to think about what training we needed and how we might make use of the exciting possibilities of machine learning. As we developed a new corporate strategy for the Met Office and a research and innovation strategy, there was a strand in that which now incorporated data science and machine learning, and you'll be able to hear more about that in one of the plenary talks later in the week from Professor Stephen Belcher, so I recommend that. But one of the elements of that strategy was to develop the community into a more formal community of practice to support the use of data science. And so we got going, and one of the initial challenges in setting up the community of practice was, where do we pitch our activities? There's such a wide range of skills. Some people who only know what the name machine learning and nothing further, other people who've been involved in machine learning for a number of years, and so have quite a high level of knowledge and expertise, and many areas in between. Where do we pitch it? And so we started off our community of practice with some tutorials to get everyone up to a sort of base level at which we could then pitch future activities. And the usefulness of this is it also is now, as part of that entry point into data science, we now have these introductory sessions that anyone new to data science can use. So where are we as a community today? We meet approximately monthly, primarily with talks from a wide range of people, internal talks about projects that are on the go, new tools and tutorials. We also have a number of external speakers from partner organizations talking about their projects and generally the activities in partner organizations. We have an active social media channel where people ask questions and post ideas, new research papers, new tools, get support when they're stuck. We've also developed some of our materials into a sort of resource portal, linking both to internally developed materials like example notebooks and recordings of sessions, as well as external courses and locations to find data sets and tools. And this is organized by a volunteer, a chair and a deputy who changes every 3 to 6 months. bringing in sort of fresh blood to the leadership team and new ideas on a regular basis without making it too much of a burden to help organizers. But we've also now moved on from just having talks and seminars to trying to do more in the way of hands-on learning as part of our community. And that's one thing I want to talk a lot about today is some of our machine learning challenges that we've started doing this year. So these are inspired by Kaggle competitions, and I'm sure many of you are familiar with at least the concept of Kaggle. But for those of you who are not, Kaggle is a website that runs machine learning competitions. A person or an organization proposes a problem, provides a nicely curated data set, and specifies what they want you to predict from that data and metrics to evaluate performance. And then people submit all sorts of solutions of trained machine learning algorithms. And then whoever scores the best on some data that was set aside for evaluation purposes, according to the chosen metric, wins a competition and potentially sometimes prize money. This is not unlike the NASA tournament lab we heard about earlier, where people come together to solve problems. But in addition to the competition of solving the particular problem, these data sets and the code continues to be available afterwards, and is a fantastic hands-on learning and tutorial opportunity for people of a whole wide range of skills. And the challenge itself often draws in people from a much wider range of backgrounds than a sort of standard way of doing a project in this area might do, and is a great skills development opportunity. One thing I've not mentioned on the slide, but should have, was that it's also an opportunity to try out new platforms and tools for doing machine learning and data science. So without sort of the pressure of deliverables, these challenges offer you an opportunity to try things out in a sort of more open-ended way as well, and feed that back to the people that develop the tools and platforms for your organization. And we'll see that links to one of the sessions, some of the sessions later this week about tools and data sets, how these are an opportunity to develop that. So we've run one competition that's finished, and we're running another one, and I'll talk about those in more detail in a moment. But just to say that we're always looking for developing more challenges after the successes we've had so far. So we'd welcome any suggestions from partners who'd like to propose a challenge that we might run together. So do get in contact if you've got some ideas there. So looking in more detail at some of these challenges, our first challenge, which was run the first part of this year, was about predicting cloud-based height from the output from our atmospheric model, the unified model developed by the Met Office. And the idea with this was that was a real problem. There are solutions that are non-machine learning for calculating the cloud-based height from parameters, but it was a manageable size problem, but a real challenge. So using temperature, humidity, and pressure at a particular location across throughout all the levels of the atmosphere, and predicting the one level that is the base height of the clouds. And so there's an opportunity for people from across the Met Office to have a go at using output from our atmospheric models for machine learning, which is something that's often not featured in sort of generic machine learning tutorials, data that's specific to the weather and climate context. So this gave people an opportunity to get their hands dirty in that way. And so this ran over a few months. Participants got together regularly. The person who proposed the challenge, Cyril Mulcret, provided a curated data set, some of which he held back for later evaluation, and a metric. He used the symmetric extremal dependence index, which is suitable for rare events or extreme events. And over the course of the challenge, from his initial naive implementation, which he provided as example code, participants were able to increase that metric quite noticeably. And so they learned a lot about using atmospheric data for machine learning, but also improved the output from the algorithm. So it was a great output from this challenge, and enthused a lot of people about this sort of problem. And people learned a lot along the way. And in fact, it's now been written up into a paper, both about the challenge itself and how it was run, that has gone into the Weather magazine. So that was our first challenge. So this was more like a traditional Kaggle style competition, in that you have some data and you can measure who won the competition. Our second challenge is more open-ended. So this has been proposed now from the operations side of our organization rather than research, looking at some challenges faced by operational meteorologists in delivering the information needed by our customers. So two parts to this problem. The first one is around strong wind gusts that affect aviation in the Falkland Islands. So you can see on the right-hand side here, the orography of the Falkland Islands. We have some mountains, and just below that is where the airfield is, and when there's a northerly wind, this can affect aviation. But they're quite small scale features affected by orography that's not captured in our model. This is a much higher resolution plot than our model. So can we infer from our coarse-grained global model local scale features using machine learning? So it's about exploring that data and finding what we can do there. And similarly, operational meteorologists observe that traffic levels on the road network are affected by the weather, as you might expect. But can we predict a sort of anomaly due to weather in traffic patterns from the data? So both of these, there's no sort of strict, you have to predict this from that and measure it by this metric. It's more sort of open-ended exploration of what's possible, with the idea that hopefully at the end of the challenge, we have some ideas and prototypes which can be further developed in a more traditional project structure and funded way to become products that are used by operational meteorologists. So these are very exciting ways to get people involved, and particularly in this one, it's a great opportunity for people who are perhaps more from the research end of the organization to get just some understanding of what the challenges faced by operational staff are and how machine learning might be used in quite a different context, and how weather data is used can be turned into those sorts of go, no-go sort of decisions that were talked about in the plenary session earlier. So quite a different context. But there are other activities also on the go. So I talked earlier about developing best practices. So a group from the community has been funded now to develop some documents to talk about what's the best way to do machine learning for weather and climate, thinking about ethics and technical infrastructure and all the various different aspects of this. And the idea is that this will now become something that's owned by the community and adopted by the community for machine learning projects going forward. And so we're not starting from scratch. There's lots and lots of guidance out there already about machine learning best practices. But as has been alluded to in others already, how do we interpret that in the particular context of weather and climate, where perhaps there's been less activity than in other sectors? So that's how we're developing some best practices. We also organizing ourselves to keep on top of the huge volume of literature and new tools that is available about machine learning, and kind of be better coordinated through sort of a journal club and regular sort of digest summaries of the most important research in machine learning. Another activity is we're putting together a data science advocates program. The idea here is that they're a sort of friendly face for the community. People who are brand new to machine learning and data science have a point of contact where they can have an informal chat and be pointed towards the most appropriate resources or courses or tools for a project where they want to apply data science and machine learning. So those are just getting started within our community of practice as a further way for people to do hands-on learning and get guidance on projects that they're doing. But this, of course, is something that we have in common, as I'm sure we'll see over the rest of the session, with many other organizations who are on parallel journeys ahead of us in some ways and have something that can learn from us in other ways. And so we really want to focus on linking with those organizations so that we share our resources and our knowledge and our expertise, and not all do everything over and over again in parallel. And so we're putting together a network of data science communities focused initially on our partners in universities, national meteorological services, and other research institutes to facilitate those connections and collaborations. And so we're starting with a sort of resource page on GitHub and an Office 365 group to have a calendar to invite people to community events. And so if you're interested in joining up with this network of data science communities, do get in touch with us. We're looking to involve all sorts of people from across the earth science community. So sort of to close off my presentation, I thought I'd just reflect on some of our lessons from the last year and a half of our community of practice, in terms of what makes a successful community of practice, not just in terms of the community in isolation, but in terms of a community that supports the wider goals of our organization. So the first one, I think, is a clear focus. Be clear about what you're doing and what you're not doing. Initially, we had lots and lots of really good ideas for what to do in our community, but we decided to focus on getting up and running with talks and seminars as being quite a daunting undertaking, and then expanding later. So be clear about what you're doing and what you're not doing, and do what your focus areas well. That's important, I think, in being successful. But also thinking about active learning. So people aren't just attending sessions and then tuning out and not really able to translate what they're doing into the areas that they're actually working on. So active learning, like challenges and competitions, is a great way for people to really get stuck into what they've heard in talks. It's also important to think about how you can be inclusive and open in your community. So it's very easy for communities to become dominated by a sort of small group of sort of senior people. Really think about how you can invite people who are perhaps new to data science or the organization, or more junior, to get involved and give talks and tutorials. But also think about different learning styles and personality types. What sort of content and sessions would appeal to different sorts of people, and include some variety. It's also important in everything you do to have community ownership of everything, so that people feel that the community is moving in a direction that is good for the community and people are happy with and are delivering what people in the community actually want. And part of that is having sort of rotating leadership, so you get lots of involvement in that. But at the same time, if a community of 150 people can't do everything collectively, you have to have some well-defined roles for people to lead it. So who's going to organize the meetings, who's going to curate your community website or SharePoint site, whatever you use, who's going to coordinate challenges and hackathons. It's important to have well-defined roles. But ultimately, in order to be successful, it's got to be supporting projects in the organization. So you've got to have support from your organization for what you're trying to do, and good connections, not just be going off doing on your own tangent. But at the same time, make sure that it is a friendly, welcoming community where people can explore new things, so outside the pressures of day-to-day delivery. And that way you'll have a successful community. So in 1 minute, thank you. Where do we see this going? So we hope to continue to develop skills and capacity through these various learning activities that I've mentioned today, and continue to grow that range of activities. And through that, facilitate projects in data science through these best practices and new skills. We hope to grow our links to other communities so we can all learn from each other across the data science community for Earth Sciences. And raise the profile of data science both in the Met Office and the wider weather and climate science community, and ultimately embed data science in that community as a key tool in the toolbox available to researchers and operational meteorologists going forward. Thank you.
Excellent. Thank you so much, Stephen. What a great start to our session. So as I explained at the beginning, we now have 2 minutes and before we move on to the next presentation, which will be by Amy McGovern. In these 2 minutes, this is a chance for all delegates to catch their breath, to reflect on Stephen's presentation, possibly to write some questions that they would like to ask Stephen and pop them in the Slack channel. As I've mentioned, the Slack channel is channel 5. If anybody has any trouble locating it, then let us know. But I'm not going to fill your 2 minutes with me speaking. I'm now going to just allow everybody who's got 2 minutes, grab a cup of tea or reflect on the talk. These are your 2 minutes to catch your breath, have a think about what we've just heard, and we look forward to hearing from Amy in about 2 minutes time. So Amy, if you'd like to...
Your second speaker appeared. So I am now back to where my normal slot was.
Oh, well, okay. Mesut, are you okay to give your presentation at 11:12?
Yes, I'm ready. Sorry, I had internet issues connecting today, so I came in and out, but I think everything is working okay now. Thank you.
That's absolutely fine. Happens to me all the time. So if you could load up your presentation, but please don't start until 11:12. I will give you a sign when we're ready to begin again.
Sounds good. Thank you.
Right, so it's just turned 11:12. Mesut, if you're okay to begin, and I'll give you a 1-minute warning at the end. The presentation slot is 10 minutes. Thank you.
Okay.
Over to you, Mesut.
Thank you. I'm trying to load this, not seeing my files. Let me see. 1 second. I'm sorry. I don't know why I'm not seeing my presentation. Ah, here it is. Okay, wonderful. Are you able to see? Awesome. Okay.
Yes, we are.
Hi, everyone. We had a great start today with some work being done related to artificial intelligence. My presentation is today more on representing my background related to the implications of AI in general to workforce development and education, which hopefully you'll find some insights pertaining to your unique areas of specialty and expertise as this phenomenon takes shape and impacts us in our fields. I'm Mesut Akdere. I'm a professor of human resource development and interim associate dean for research at Purdue University, Purdue Polytechnic Institute, one of the colleges here at Purdue West Lafayette. Today, my topic is the global artificial intelligence transformation and its implications for workforce development and education. As we know, the challenge we are facing is that AI is introducing unprecedented challenges to the society, the workplaces, and work itself. Very frequently we see different ways AI is kind of filtering into our lives or the work we do. Recently, I've had an opportunity with work with someone on a research collaboration, and actually instead of to assist her work, she was using an AI which will help scheduling and other aspects, and it was kind of interesting experience for me just to see how that in some ways helps us, but then in other ways how it eliminates the human aspects of some of the experience I would typically gather through research collaborations. And obviously, this is a phenomenon that takes place all over the world, not just unique here in the United States. We see the significant growth in AI, the big data utilization, especially with big tech companies. Sometimes I start to think that I know that they're listening to us, but then as soon as I think of something that appears, and that's where it gets scary in a joking side, but these technologies are becoming really powerful and beginning to kind of filter into our workspaces and impacting workers. On one hand, most of the companies that may see the benefit of incorporating some sort of AI component into their work, into their production or services or whatever that might be, in order to increase their efficiency or productivity or quality of their products and services, this may seem like a great idea to them because of their concern to, be competitive in a very global environment. On the other hand, we have the worker side of this, where people are very often asked to work, change, adapt to new ways of doing things at work. But then with AI, we start to become more aware of how our personal information is being used. This persistent monitoring, how actually it will impact where that information or any information for that matter that is collected as part of this a workplace process might be used later on. These are some of the immediate concerns, but also people start to think, well, what would happen if my job is being replaced by one of these or reduced to something else because of this? In fact, even in the world of medicine, some physicians begin to wonder how long it will take for AI to totally take over most of the work done by physicians, and actually, especially in the diagnosis stages, that they have a greater capacity to look into the symptoms and come up with or examinations and analyze and identify potential diagnosis. So the impact of AI is across all industries. That's undisputable fact of today. Unfortunately, neither any government or organizations are also adequately equipped to effectively manage these transitions, because here we have a phenomenon that is impacting the people's life, impacting the way they do work, impacting the way they live, but then we don't have systems in place that would immediately address any concerns or issues or look into this. And then, so there's a gap in this, and this, the technology expansion will continue, and it's inevitable for that. And the potential impact of the adverse impact of this is going to be very significant, because it also begins to impact the workers adversely, and also educate workers because of the stress it may pose or other concerns that the AI might pose over the way they work or other work-related issues. And as a result, we may see larger impacts of AI even in a broader workforce in various fields, depending on the speed and the interruption AI might bring to that particular industry. But we are in a great position as research communities to study these potential impacts in our given fields. And also, as we are doing this, one of my message in this presentation is that we kind of keep in mind how that might impact the people that actually does the work in your fields. That not just from a research side, but people actually practicing how that might work, impact the workers, the labor market, even industries in a global scale. On this note, and one of the related notion is that I want to share here is the principles on AI is by the Organization for Economic Cooperation and Development, that is OECD. They have 5 recommendations that they talk about. Particularly, there's a complementary values-based principles for responsible stewardship of trustworthy AI. So as we are designing, as we are incorporating AI into work, whether we are in charge of developing algorithms or in charge of utilizing that algorithm into our work. These are some of the principles that might be shared. In the interest of time, I'll briefly mention them here, but these 5 principles is something I find very useful and applicable across all industries and contexts. They also have recommendations for governments from a policy standpoint, and these recommendations can also be taken into account for the various organizations, such as this one we are participating today, that ensuring policies are in place to protect, human well-being, and as we are looking into maximizing the affordances of AI technologies, but also maintaining especially ethical values and value ethics and values that we adhere.
1 minute, please, Mesut.
Sure. And so the solution is that as we are looking into the future, the most successful workforce of the future will have data literacy, machine learning, and data science expertise, and the capacity to implement and manage AI solutions, including environmental sciences. So the need for the AI should be addressed at the workforce, and educational issues are coming upon us in these fields. And we have to identify complementary approaches to more specifically address workforce-related policy issues and how these transitions can be successfully achieved. Obviously, the focus here is both on the preparing a future workforce that is competent working with AI-related technologies, but also encouraging policymakers to identify policies that would protect us humans as we embrace these new technologies. I think I'll stop there. Thank you.
That was excellent. Thank you very much, Mesut. Lots for us to think about there. So we're getting into the rhythm of this session now. So now all the delegates have 2 minutes to reflect on Mesut's presentation, to think about any questions you may have for him, and to put them in the Slack channel. During this 2 minutes, can I also encourage all of the speakers to have a look at the Slack channel? These are questions that may be coming your way, or you may like to try and write some answers in the Slack channel now. So let's get that conversation going. If everyone could keep an eye on the Slack channel. Amy, if you wouldn't mind loading up your slides, we should be ready to start in about 1.5 minutes time. Thank you.
They should already be loaded and shared. I'm assuming you can see them.
Looking good. So if you just hold fire for another minute while everybody has a chance to reflect on Mesut's presentation. Thank you.
And Mesut, you do have a question that has popped up in the Slack channel, so make sure to check that out, and just again encouraging others to drop their questions or just general chatter in there. Thanks.
Sure, Annie. Yes, I actually saw the question and I'm typing
awesome.
it. Thank you.
Okay, great.
And Amy, when you're ready, please do begin. Thank you.
Okay, great. I'm going to take a little bit of a different tactic than the last two talks. So I'm giving a little bit more research update than the community update, but I'm glad to talk about the community aspect as well. So I am the director for the NSF AI Institute for Research on Trustworthy AI and Weather, Climate, and Coastal Oceanography. We are the AI Institute that was called out this morning in the talk, in the plenary. And in the interest of time, I am not going to list all our partners. They are all on this slide. And if slides will advance. Okay, so I have entirely too many slides for 10 minutes. So what I'm going to do is try to focus on just a few of them, and then the slides are all going to be available at the end. We have in our research section of what we're working on, we have 3 different focuses. We have foundational research in trustworthy AI and machine learning. We have use-inspired research that are all focused on environmental science domains that are shown there. And then we have the risk communication research. And those 3 work together hand in hand in a cycle where the risk communication is helping inform what we're doing for the trustworthy AI to actually make sure that it's really trustworthy. That question this morning about what makes trustworthy AI was not my question, but it was a perfect question. And we will be talking about that a little bit. We also have broadening participation in workforce development, and I don't want to miss that, especially since this is the community practice session. But I want to hopefully have time to give you a quick update on what we've been doing. We've been around for a year now. In the nature of time, I'll skip this particular slide. We're focused in right on some of our results that we have. We have been focused on the nature of the foundational AI and machine learning. We've got XAI is one of the things that we are working on, and we have a talk tomorrow that'll be talking about, actually that's in 2 slides that I'll highlight that talk. We have a couple of papers that are under review looking at developing benchmarks for XAI methods for environmental science specifically, because XAI as it's developed generally speaking, is on images and not using environmental science data, and there's different needs for environmental science data. So looking at what's different and what we need to do to make it work for different environmental science or science applications. This is the one that I was jumping to in my brain already. There's a highlight talk at this conference tomorrow, Tuesday, on how to develop loss functions for neural networks for environmental science applications. And you can get the paper from arXiv from this slide, but I encourage you to come to the talk, and they actually get more than 10 minutes, they get 20 minutes, so go to that. And pursuant to the discussion that we've been having about giving out code and doing a community of practice, they already have a GitHub repository and you can download all the code for this. Another update from our foundational AI and machine learning, some methods that are under review right now from Libby Barnes on incorporating uncertainty into the learning. So trying to figure out how to say that you're confident about one example and then maybe less confident about another example, and how can you use that confidence in your learning to improve your learning method. Somebody else is unmuted. I can hear other noises. Finally, in our foundational AI and machine learning update, looking at some of the robustness and the theoretical aspects of our learning. One of the things that we're trying to do beyond the XAI and beyond physics-based AI, which I didn't have time to talk about, is we're trying to make sure that what we're doing is robust both theoretically and empirically. And so we have a paper out already on looking at PAC learning, which is probably approximately correct learning for those who are not computer scientists, with high recall and high precision. So this is a very theoretical paper, but focusing on how we can make our very robust in imbalanced data sets, which is something that we have a lot of in earth sciences. Moving quickly to what we're doing, once we've got the foundational research started, what are the different areas that we're applying this to inside environmental science? We have 5 different areas. The first is convective weather, where we are developing, for example, the last year we've been working on developing machine learning based nowcasting systems. So that is specifically in the very near term for tornadoes in the 0 to 1 hour, hail in the 0 to 3 hour. We're developing XAI to make sure that what we learn is physically plausible. And we have a paper under review for all of this. It's the same place that the other paper I mentioned has been under review. It's been under review for a very long time. It's a special issue of a journal. Hopefully those results will be out soon. We are using convective weather for our prototype use case for the synergy between AI and risk communication. So we're also starting our interviews with the forecasters with the convective weather cases. Winter weather, we're looking at a variety of different applications over the summer. We were working on doing image detection of trying to predict precipitation type. What is falling? Is it rain? Is it snow? Is it nothing? And then visibility. This was joint work with between Albany and OU. And they have a whole bunch of camera images on the New York State Mesonet that are underused. And you can imagine that if you could use these New York State Mesonet images, which are very stable, we could also then apply them to potentially other public cameras to figure out visibility more broad spread and precipitation type, and we get very fine scale information about our weather. Our third use case, looking at tropical cyclones. Here we're using AI to generate synthetic microwave imagery because the data that's available in real time, or there are different satellites that are going over the tropical cyclones. Some of them can see the data in only twice a day. Some of them can see them every 15 minutes, depending on which satellite it is. And we're trying to use AI to generate the more frequent data from the data that's available less frequently, and then use XAI to make sure what is learned is actually physically plausible. The fourth application area is subseasonal to seasonal prediction. And here, this is an example of where we're using the I don't know networks, the uncertainty learning, as well as abstention networks, and working on doing climate scale predictions. The fifth application area is coastal oceanography. Here we're looking at a variety of use cases. I highlighted just for this slide, one network called FogNet that is a physics-based AI network that does fog prediction in Corpus Christi. And then another network, which is working, it's just a more simple network, it's just a regular neural network, not a whole convolutional deep learning network, that is doing prediction of the cold stunning temperatures, like the event that happened in February that everybody remembers when it was really, really cold. When it gets really cold, the turtles are cold stunned, they rise up to the surface, they can get run over by the ships. If you have a reliable and trustworthy network that actually tells you when those cold stunnings are about to happen, then you can actually stop the traffic and save lives. So it's another impact that we can do with our AI. Another coastal oceanography application that we're looking at harmful algal blooms, and ocean eddy prediction, and working on creating a very large scale data set for this that will be available as well later, very soon. Sorry, trying to get through all these slides in 19 minutes and I'm talking too quickly. The final aspect of our cycle is working on the foundational research in the risk communication. And in the risk communication, I said that this was one of the keys to what we're doing, because the AI people can develop their AI, but if they're doing it in the dark or even just hand in hand with the environmental scientists, they don't necessarily know what the end users think about the AI and why they would trust it and why they don't trust it. And the risk communication and the social science aspect is really, really key, because it's going to tell us why people actually trust what we're doing, or likewise, if they don't trust what we're doing, why they don't trust it, and what we can do to inform our AI to make that better. And this gets to that fundamental question that was asked earlier about what does trustworthy mean? We really need to talk to our end users from the beginning to figure out what it means to be trusted and useful. And so we are in this first year, we've developed an interview guide, and we are in the process of doing pre-tests and just transitioning into the regular full-scale interviews of what it means to be trustworthy, what the end users, who are mostly forecasters and emergency managers, what their perceptions and attitudes of AI are, and why they might trust AI and why they might not, and what we need to do to move that into our methods. So a quote that comes in here, the first word that comes to mind is reliability. When you said trustworthiness, I'm thinking in my head, almost like in a verification sense. You're thinking, is this reliable? Is it reliable in my part of the domain? So we need to think about that while we're making our AI methods. And I said I didn't because this is community practice. I wanted to make sure that I got to the ending slides. The education and workforce development is a key part of what we're doing. We are an NSF Institute. We are not just focusing on the research, we're focusing on workforce development and broadening the participation broadly across all of AI and environmental sciences. So our fourth goal is to improve both at all levels, K through 20, and workforce retraining, to improve the diversity of the AI and the environmental science workforce. And I know that Dr. Parker mentioned this in her talk this morning, but I am going to bring it up because it is one of the first. Okay, 1 minute. Well, that's great, because I'm on the second to last slide. I'm good. One of the first AI curriculums at a community college level was started just a couple of weeks ago. So it's an occupational skills award. It's 14 hours of credit, and you can learn about AI. This is designed for high school students who are doing concurrent enrollment, people who are going to community college in general, people who might be coming back, looking at community college, coming from the workforce, all of those. They get this occupational skills award, and it can feed into a later bachelor's degree if they want through TAM-UCC, through a cooperative agreement there. And we're developing this at a Hispanic serving institution, minority serving institution, with the goal of making sure that we are improving diversity, and then we will take this nationwide. And because I get 20 seconds left, this is my final slide. Just want to say that AI for Environmental Science is happy to take more people who are interested in working with us. My long-term vision is that we will create a multi-agency, multi-sector center that will help us with both weather and climate issues. And we look forward to having more partnerships and more discussions. So thank you.
Oh, thank you very much, Amy. That was a real whistle-stop tour. So if I could just remind all delegates, you now have 2 minutes to reflect on the material that Amy's just covered, to think about any questions you may have and pop them in the Slack channel, and to think about how this might be relevant to your organization. And can I also highlight that both Amy and Stephen before her put a call out if anybody is interested in working with their organisation. So Stephen invited different organisations to join the community of practice, or the network of community of practice, and Amy's put a call out as well. So please I encourage everybody to put information to the Slack channel so that we can get the conversation going. And we'll start with the next presentation in about a minute's time. If I could ask David Gagne to load up his slides, but no need to start just yet, David. We've got a minute for everyone to reflect and to think about what they'd like to put into the Slack channel. Thank you. And thank you again, Amy. That was excellent. And David, when you're ready, if you'd like to begin, and I'll give you a 1-minute warning after 9 minutes. Over to you.
All right, good morning, everyone. My name is David John Gagne. I'm a machine learning scientist at the National Center for Atmospheric Research. Today, I'm going to talk about the NCAR Analytics and Integrated Machine Learning Group and kind of provide an overview of our research and our sort of philosophy behind what we're trying to do at NCAR with machine learning research. So first, I'd like to talk about the overall kind of mission of our group. What we're trying to do is integrate machine learning throughout the community Earth. Throughout community Earth system science modeling and observation pipelines with kind of 3 underlying goals in mind. And these are meant to be kind of tied in with the overall mission of NCAR. First part of that is to refine our understanding of their system, learn more about the underlying processes that drive weather and climate. We want to, through that, improve our prediction of weather and climate phenomena and their associated impacts. So not just making a better hurricane prediction, but also understanding like how does that affect people on the ground and all the associated factors, including societal factors. And finally, want to be able to enhance the capabilities of our community observation and modeling computing facilities. This is including things like accelerating AI or accelerating our numerical models and our observation platforms so that we can collect more observations, build better models, and so on. Here's a selection of kind of part of our core group. While we're nominally based in the Computational Information Systems Lab at NCAR, our interest and collaboration span across all labs and across multiple disciplines. So our core members also don't just sit and sizzle, but have connections throughout not only the labs, but also the university community. So I'm personally jointly appointed with the Research Applications Lab. We also have Maria Molina, for instance, as a project scientist in CGD. We have quite a few student assistants, grad students, and postdocs who join us from all over the place. We also have a diverse array of expertise. We have people who come from not just like an atmospheric science background, but also physics and chemistry, kind of economics, data science, social science, and thus by bringing this like kind of diverse expertise together and have people who are used to kind of talking across domains, we're, I think, better able to support all the broad array of collaborations that we're dealing with on a daily basis. So kind of our main research areas include things like more traditional machine learning problems like feature analysis. How can we track storms better, identify storm types? How can we process images and extract the information within those images? And dealing with processing data in both weather and climate models. On the emulation front, we have a number of projects spanning weather, climate, and atmospheric chemistry areas that are looking at ways to emulate complex atmospheric models and allow us to basically run models that we couldn't normally run in a full-scale weather or climate model with machine learning emulation. One of our ongoing areas beyond this is also predicting high impact weather. A lot of this is currently focused on sort of post-processing numerical weather prediction models and observations to come up with better nowcasts and forecasts of extreme weather. But we're also interested in things like risk modeling. How do we translate the weather phenomena down to the surface and the people that are affected, as well as other kind of downscaling applications to get a finer grained sense of what's going on at the surface. We're also a partner in the AI2ES, as in our previous talk by Dr. Amy McGovern. In particular, we want to work on within their explainable AI, physics-based AI, and uncertainty quantification. Finally, one of the big missions we see ourselves doing is educating NCAR and the broader atmospheric science community on how best to use AI at the intersection of Earth system science. One of our big events was the AI for Earth System Science Summer School held last summer, where we had thousands of attendees from around the world attend the kind of a week-long virtual workshop to learn about all the different aspects of AI for system science, as well as doing hackathons and producing new data sets. For more intensive mentoring, we've hosted quite a few graduate visitors, postdocs, and have had other interns, and we'll continue to support more internships through like NCAR's many different internship programs. So what kind of makes a good integrative collaboration? So we, in order to work across all these areas, we have to work with a lot of domain experts, because we just don't have the expertise in all these different fields to really do them well. So we find that a good collaboration, one, needs to engage both the machine learning side and the kind of domain side. And we have to spend a lot of time communicating. We have to develop a shared context of how how the problems form, what the data look like, what people care about on both sides, what are the challenges. And we do this through a lot of Zoom meetings, a lot of making sure we regularly get together and hash out all of our challenges and share results and work through these problems. To make this scalable, though, we've had to figure out how to do more parallel development, have some more clear handoff points, so we can say, here's our machine learning model, you can put into your numerical model, run it, get back to us. Okay, now we can iterate, and we can do this larger cycle, as well as cycling within each of our sides, and along the way develop better goals and metrics, and track progress over the iteration, so we make sure we're actually moving forward. This is, I think, worked well. We've made progress in a lot of these areas, but we've definitely run into quite a few challenges in integrating machine learning into a lot of problems. One is just proposing projects that push the limits on both the machine learning and the domain science sides, where there's a lot of instances where we might want to try a really cool machine learning problem or use a more complex algorithm, but the data we want to use on may not be the biggest challenge on the domain science side, or the biggest challenge on the domain science side is related to stuff where we don't have a lot of data, where doing machine learning is really hard. We've run into a lot of data challenges, not just with observational data, but also with model output. There's a lot of cases where little small details about how the numerical model runs were set up make a big difference in what kind of relationship we find between the available inputs and outputs. Sometimes we discover in the process of trying to do machine learning with physical constraints that the data itself did not obey said physical constraints. So that's another point where we have to iterate and work with our domain partners to kind of identify these issues, which may not have been found if we hadn't done the machine learning in the first place. And of course, there's always noisy and biased ground truth data, which isn't always really ground truth. And knowing what's causing those biases and issues is really important to trying to address them in different ways. There's also a lot of issues with, I think, training and evaluation. The one I wanted to highlight is that sometimes there's little correspondence between whatever your test set area under the rock curve or accuracy is and what the real-time performance is inside another modeling system. And so we have to iterate a lot on this and figure out how far we can iterate with given funding and time to get a good enough result. We're also trying to use explainable AI and understand what it means in different physical science contexts. And now we're at the point where we have a number of projects that have reached a certain level of maturity, and we're trying to figure out what's the next step. Who do we hand this off to continue to develop and maintain, so that we can continue to look at other cutting edge problems. So it's I think a challenge that a lot of other AI organizations are also dealing with. Finally, I wanted to highlight a few of the talks our group is giving at the AI workshop this week. First, on Tuesday morning, I encourage you to check out Gabriel Gantos's poster on processing holographic images. We're trying to take the holograms generated by a cloud particle imager and process them with a deep learning model. And so we get some cool 3D circle pictures like this to represent different sizes of raindrops. We have our atmospheric chemistry emulation project is going to be highlighted by John Schreck. So we'll learn about
1 minute now, please, David.
Thank you.
Thank you.
So you'll learn about using explainable AI and time series models here. Charlie Becker on Wednesday is going to talk about using deep learning to classify storm mode, and you can see a preliminary result here where the storm hazard is in fact linked to mode as predicted by the deep learning model. Finally, we have two of our students are also giving talks. Shiheng Duan is giving a talk on predicting snow water equivalent with machine learning and highlighting some issues with the training data biases. And Yingkai Kyle Shah is also giving a talk on his new paper using CNNs combined with analog ensemble to create better bias corrected and smoother model output. Finally, a couple of things I wanted to highlight at NCAR going forward. We're going to be releasing a new web portal hosting a number of AI data sets in the next few weeks. We also have a new supercomputer coming online, Derecho, that will be featuring a lot of GPUs. That will be great for really scaling up some of our deep learning problems. So I'll leave you with our final slide of next steps and go into questions.
Thank you very much, David. So we're definitely all getting into the routine now. So it's 2 minutes for reflection for the attendees. And you might like to take this 2 minutes to not only think about David's talk and the content and what questions you might have, but also possibly to update your schedule for the rest of the workshop. Amy and David and Stephen have all highlighted talks that are going to be coming up that you might wish to attend showing the richness of this conference to really get the most out of this conference experience. So if you take these 2 minutes now to reflect, update your schedule or grab a cup of tea. And can I encourage everybody to keep an eye on the Slack channel, including the speakers, because there's some quite lively debate going on there about different questions to do with the talk so far. Andrew Nang, if I could ask you to load up your presentation, and we'll start in about a minute's time. Thank you.
Hi, everyone. Just a note from the Logistic Organizing Committee. We do have live transcript closed captioning capability enabled for all of our sessions. So if you're looking for that, you should be able to find that button. There are two options there, subtitle version and also a view full transcript along with additional settings if you need to change something. So just so you know, if you haven't caught that feature already.
Brilliant. Thanks, Chris. Andrew, if you'd like to begin when you're ready, and I'll give you a note at 9 minutes. Thank you.
Absolutely. So good morning from Seattle. My name is Andrew Nang, and I'm a PhD student from the Department of Human-Centered Design Engineering at the University of Washington. And today I'll be presenting some ongoing research work centered around how ocean science researchers assemble heterogeneous data sets for machine learning. This work is part of a larger study supported by the NSF and done in close collaborations with my colleagues here at UW, listed here. So, like many other scientific fields, oceanography is witnessing a data explosion, with new instruments enabling the generation of vast amounts of data, both from samples obtained out at sea and also remotely, such as with satellites. As a result, cross-disciplinary efforts to integrate different insights and methods have become more important than ever to addressing long-standing scientific challenges. However, such obstacles to cross-disciplinary research can come in many forms, whether it be different methods, languages, scientific interest, and even, I want to emphasize, even the most mundane issues such as how data are formatted. So as part of our study here, we approach these problems as a matter of learning heterogeneous knowledges, or more specifically, in the language of community practice, what is called legitimate peripheral participation, which I'll be discussing in more detail. So for the past 3 years, I've been following a group of ocean science researchers and data scientists that are part of this multi-institution effort called Mahalo. This collaboration seeks to investigate the way daily cycles of light and dark, also referred to as the diel, act as fundamental controls on how the microbial community in the surface ocean operates. And the majority of data sets generated by Mahalo researchers come from utilizing an array of so-called omics approaches, as you can see in the left panel here. Lipidomics, transcriptomics, metabolomics, all of which are important tools for helping understand the biology of an organism and its response to other environmental drivers. And so the work of interconnecting these diverse time series data sets so that it can provide a coherent view of the diel light cycle is an essential step for Mahalo researchers to be able to explore how these light cycles affect microbial communities and carbon fixation. This work is like neither straightforward nor easy, as there were many unexpected and unforeseeable challenges that surfaced. And through this work of integrating these diverse data sets, Mahalo researchers quickly realized that extracting meaningful scientific insights was extremely complicated. As a result, researchers sought to discover more scientifically meaningful ways to partition and characterize the temporal dynamics of marine microbe activities beyond what we think of as just night and day or in 12-hour intervals by employing machine learning methods. So as mentioned earlier, I've been embedded in this research group for quite some time. And for this research work, as well as our larger NSF-supported project, I've employed a number of ethnographic methods, which include participant observations of group meetings, presentations, demos, as well as conducting semi-structured interviews with researchers on an individual level. And also as part of this work, I have also collected and analyzed historical archival data in the form of what you see in these icons here as code, emails, and documents, all of which to kind of help me supplement my understanding of the nature of the work that's unfolding. And so we know that communities practice are often described as groups of people who share a concern or a set of problems and who deepen their knowledge and expertise in an area by interacting on an ongoing basis. One central focus of talking about communities of practice is to examine the process of learning. And so the notion of communities of practice really provides us a way to talk about apprenticeship, or what is sometimes referred to as legitimate peripheral participation, which I'll refer to as LPP as sort of a shorthand going forward. So we can see in this diagram here, there's a core and there's a periphery. And the domain experts in the core are important as they help codify and transfer knowledge. They also assist members in understanding culture and practices within the community. Then we have newcomers over here, and they sort of have a legitimate membership and are allowed to be slowly pulled in over time. And this is something, just to kind of crystallize, is something that we have observed in many kinds of field sites. Some things that you all might be aware of as well, where we've seen it in terms of medical interns, people in the trade industry, such as carpenters, and of course, graduate students as well. And so one of the major things I want to talk about is also one of the central actors I've been following as part of the Mahalo collaboration is an individual by the name of Daniel, who's sitting over here on the left. Daniel's a PhD student in quantitative biosciences and serves as both as the data scientist and lead on this data integration endeavor. And to really illustrate how LPP unfolds in this context, I'm going to go deep into one instance of a problem Daniel encountered and how he worked through it. And then I'm going to move across some other unexpected and unforeseeable challenges that Daniel encountered. So one of the major challenges that Daniel faced early on in the process of trying to pull together these diverse data sets was trying to figure out how to handle the differences in the number of technical replicates employed by researchers during the data collection process, so when they were out at sea. Some labs have a preference for duplicates while others prefer triplicates. And so just to clarify, technical replicates are basically repeated measurements of the same sample that represent sort of independent measures of the random noise associated with the protocol or equipment. And in this situation we see here, Daniel's actually working closely with a chemical oceanographer PhD student by the name of Angie, who's centered here as the domain expert, to really try to understand how to interpret and handle sort of her metabolite data set properly. And Daniel shares the following in an interview in regards to this work here. So we had a conversation where I was like, can you just please explain like every single thing means? This was the first of many conversations we would have about how to handle the data properly. Angie definitely saw red flags the moment I mentioned treating the 3 replicates as linked. I was pretty embarrassed since I really thought they were connected throughout our earlier discussions. We can see here that working towards becoming a legitimate peripheral participant in this situation is not easy for Daniel. And that this misinterpretation of the replicates being linked has consequences for the analysis. It is also somewhat an embarrassing situation to be in to have to be corrected. And to address this problem, Daniel has to assume the role of an apprentice in an area well outside of his expertise, in an area that he never even imagined needing to deepen his knowledge in. Angie also, who works as a domain expert in this situation, also expressed her concern around this issue by sharing, there are 3 replicates that are all sort of their own thing. And I was very concerned for a day when he sent me an email that implied that. I was like, we need to talk because that could lead to you to interpret the data differently. Clearly, to address this problem here, multiple engagements in the form of conference calls, emails, exchanges were necessary to help Daniel learn how to address this problem and ensure observations across all of Angie's replicates were used for determination of periodicity. It's also important to note that the challenge that Daniel faces is not only just scientific in nature, but also one of coordinative work to ensure that he could properly engage and learn from Angie. There's also a level of emotional difficulty that needs to also be recognized that comes with this kind of work. And so in order to get the time series data in a state where you can employ machine learning to partition and interpret the data, Daniel had to continue to work in engaging other collaborators, as we see sort of this animation here, and resolving problems that he would have to surface along the way of leading this data integration efforts. Examples of these challenges include, that were encountered include understanding how to handle missing values with the data sets, learning how to pull together different data sets, different data and time string formats, I should say, but also discovering how to make different transcriptome data sets comparable that were originally analyzed at different taxonomic levels.
1 minute, please, Andrew.
It's important to note that this is an ongoing heterogeneous in the sense that it's simultaneously a scientific, technical, and coordinative work challenge. There are a variety of these problems, and they're not the same, most of which are not predictable beforehand. And so I really just want to leave with this closing point that in the activity of assembling heterogeneous data for machine learning methods, participants must navigate heterogeneous expertise well outside their own. And to do so, they must engage in multiple instances of being a legitimate peripheral participant, learning about technical data issues, technical scientific issues, and more ephemeral coordinative issues. And some of these contributions from this work really can help us deepen our understanding of how multidisciplinary researchers coordinate with each other to integrate data, but also create a more nuanced picture of how researchers navigate unforeseen challenges in data integration for machine learning. And definitely it's something that we look to continue our work and expand upon. So thank you, and I'm happy to take any questions as well. Thank you.
Andrew, thank you so much for your presentation. So delegates, you know the routine now. So we have 2 minutes to reflect, to put your questions into Slack, to think about how Andrew's presentation might resonate with your own work. And please, can I encourage you to think about putting some questions and comments in Slack so that we can keep the conversation going after the session ends at 1:15. And speakers can also remind you to keep an eye on Slack because there's some good questions coming in, and it would be nice for us to start answering them if we can. So we move now to our final presentation. Isaac, could I ask you to load up your presentation to start at 12 o'clock? Thank you.
Thing. All right, can everybody see it?
Yep, looks good.
Okay.
And Isaac, if you'd like to start whenever you're ready. Sorry, I said that just as you drank some water. But as soon as you're ready, feel free to start, and I'll give you a shout when we get to 9 minutes. Over to you.
Okay, perfect. Hi, my name is Isaac Passmore. So a little bit about myself. I graduated from UMBC in 2013 with a degree in mechanical engineering and received a master's degree in space systems engineering from Johns Hopkins. I started working in satellite operations about 8 years ago when I first got an internship working with the NOAA SNPP weather satellite. It was an awesome experience, and I instantly knew that I wanted to launch and fly satellites for a living. Now, I work as a ground system engineer for the GOES-R series and SWIFO satellite missions. Today, I want to talk to you about the AI tool we're developing for GOES-R, the NOAA Mission Operations Assistant. As you can probably imagine, GOES-R is a very complicated mission. We knew from the start our biggest challenge would be getting the buy-in from the user community. There's often a lot of hesitancy when adopting new technologies. We made the GOES-R community our #1 focus while developing MOA. On GOES-R, we have a big data problem. We don't really have any big data tools to help fly the satellites. So it's critical that the team responsible for producing much of the nation's weather data have the necessary tools to do their jobs effectively. Engineers and operators are expected to monitor the system 24/7. Compared to previous missions, the GOES-R weather satellite produces a ridiculous amount of data. So when operators are asked to monitor the real-time feeds, it's very easy to get overwhelmed. It can be really tricky to analyze log files that are time sensitive. And just finding the correct data can be a challenge. This is where MOA comes in. The goal of MOA is to empower system users by helping them become more self-sufficient. We want to make this system much easier to use. Let's be honest. I know I'm at an AI conference, but most other people don't know how to use a terminal, or at the very least are incredibly uncomfortable inside of one. For MOA, we wanted to focus on making the act of just finding data simpler. We want to give the users enhanced search capabilities as well as some quality of life improvements. If we were able to mitigate some limitations on the existing system, then the many smart people of NOAA and NASA could do their jobs so much better. When first starting out on MOA, we wanted to find a question worth solving. To help paint this picture, let's run through a quick hypothetical. I want each of you to imagine that you are in charge of flying a satellite. You just had your most productive Monday ever. You go to bed feeling good, and you doze off to sleep thinking about how much you love flying satellites. Suddenly, you're woken up. It's 3 a.m. The satellite operators are calling, and you realize at this precise moment, you are the very first person called when that satellite breaks. You now have exactly 5 seconds to wake up and comprehend whatever drama that is about to unfold from the other side of that phone. As you try to quickly regain consciousness, you begin to hear the alarms and sirens happening on the other side of the phone. The operators then read to you that critical message that set off this nightmare. Right now, the most important question you can ask yourself is, have we ever seen this alarm before? If you can't answer that question, there's a very real chance the next 30 minutes, you're about to get to know 10 to 20 of your coworkers really well. This could become a very long night. So being able to quickly and accurately answer, have we ever seen this alarm before, is absolutely critical. With MOA, we enable any user of the system to simply click a button and accurately answer that question. Part of what makes MOA so successful in the GOES-R mission is due to how much attention we give the GOES-R community as we develop this tool. The MOA team has fully embraced the agile development model. We make every possible effort to let the GOES-R community feel as if they are a part of the MOA team. And that's because they are. We want to make using MOA as easy as possible. We want the tool to be used in meaningful ways. We meet with different GOES-R personnel throughout the week and give them every opportunity to see, question, and suggest improvements to MOA. The live demos we give aren't rehearsed and often find new and interesting bugs right in front of everyone. We don't hide it or try to gloss over them. We want everyone to feel that they are a part of this team. By letting the GOES-R personnel see all of the progress as well as all of the parts that still need polish, we build a community of trust and openness, which is critical when developing AI in a field that is very hesitant to adopt new technologies. So let's talk about some of MOA's features. MOA is actually composed of 3 main tools that all complement each other. This is the MOA search engine. I had to redact a lot of it since this is the actual GOES-R satellite data. Otherwise, security would just have a fit. So MOA has all the standard features of a modern search engine. When a user searches for a term, they are given the results as well as a histogram of those results. This gives the users a good feeling for how their data is behaving. Next to each search result is a menu of common actions taken by people working with the log data. For example, if a user wants more context about a specific result, they just hit a button. NOAA will then take them to the original log and show them messages surrounding their original search term. Another handy feature is the Add Note button. This allows users to attach what is effectively a digital post-it note to any log message. NOAA will then attach this note to all similar messages and all future similar messages that are produced by the system. These notes can give users that extra bit of information that might help better explain an alarm that they're unfamiliar with. And these notes go a long way to cutting down on the number of phone calls for extra support. We want users to interact with NOAA as much as possible. NOAA is constantly monitoring how people interact with it. This is so we can create and refine smart filters that are being applied to the next tool. The NOAA message view is a real-time stream of logs used for system monitoring. On the left-hand side, we have the original logs as they are produced by the system. These messages can come in at rapid fire and tend to just flood the screen. It is very easy to get overwhelmed and overlook important messages. On the right-hand side, we have the AI filter view. These messages come in at a much calmer pace. Users are able to tell NOAA directly what messages they believe are important and which are worth filtering out. It's worth noting that all of the same features available inside of the search are available in message view. Additionally, the operators don't have to navigate to the search engine to perform complex searches. They simply hit a button and the search is executed, identically, regardless of who hits the button. This makes troubleshooting over the phone significantly easier, as the differences in various operator skill level becomes less pronounced. Lastly, we have the NOAA impact map. This is another real-time monitoring tool, but this one is monitoring the weather products produced by the system. Based on historical data and available log data, this tool predicts when weather products are likely to be degraded or outright missed because something failed on the processing inside the ground system. The impact map gives the engineers and operators a faster way to recognize and hone in on a problem. Like the previous tools, these log messages will have all the available notes and action items. Overall, NOAA does a great job of addressing the risks and hardships faced by the GOES-R personnel. NOAA is a big data tool designed to address GOES-R's big data problem. By focusing on the accessibility of log files, general users of the system become more capable at performing their duties. Through the use of notes, key mission knowledge is easily captured, retained, and disseminated to the entire staff when it's needed most. This dramatically helps reduce burnout faced by the traditional go-to experts. The GOES-R team is very excited about NOAA, the tool they helped build. NOAA empowers teams. If you want to learn more about NOAA and how it can help your team, please reach out. My email is on the screen. There are so many other features that I didn't get a chance to talk about, but there's one last important thing I need to mention about NOAA. NOAA is designed to be generic. After all, we're just dealing with log files here. We can easily adapt NOAA to other satellite missions, but there's nothing specific that forces NOAA to be limited to satellites or ground systems. All of these tools can be repurposed for many different industries. NOAA just needs log files. So with that, I want to thank everybody for their time. And again, if you want to learn more about NOAA and how it could help your team, please reach out. Again, my email is on the screen. Thank you and have a great rest of your workshop.
Isaac, thank you so much, and thank you for keeping so well to time. That was excellent. So I'd like to thank all of the speakers for some really interesting and presentations that were jam-packed full of information. So thank you so very much for that. And thank you also for keeping to time. Apologies, I wish I could have given you each the full hour and a half. You could easily have filled it with interesting material. So we now have 5 minutes to do a bit of question and answers. So I'm going to ask Chris if he could select 1 or 2 questions from the Slack channel that we might like to ask some of the presenters to comment on. Chris, over to you.
Yes, I think I'll recast one from Sumet Sandhu, if I pronounced that name correctly, kind of more broadly for the entire panel. So thinking about our different communities of practice, how do you see them kind of acting as a way of being part of environmental justice and helping kind of shape what that might look like?
How do you want us to answer? Just take turns? And also you're sharing a Zoom screen of me on your own Zoom screen, which is a little weird.
That might still be Isaac presenting.
Oh, okay. Well, whoever's sharing screen, there we go. So the question is how we're going to shape environmental justice?
Right, or how could we use communities of practice to do that?
I'll give a AI to a yes answer, and then I'm sure the others have answers too, which is just that we are, as the NSF Center for Trustworthy AI, we are focusing also on making sure that the AI we develop is ethical and responsible. And part of the ethical and responsible nature for us is looking at the environmental justice issue. And so making sure that what we develop is addressing the needs of everyone and not perpetuating any environmental injustices, and actively working on environmental justice issues. And I am happy to have people join us in that work, and I'll let the others answer.
One thing I can add on this is I think it's also important to bring in a diverse community of practice in terms of not just all machine learning people or all environmental science people, but like reach out to a much broader community of including people who are like affected by disasters and affected by climate change. We also may need to reframe how we're thinking about the kinds of problems we can predict. When the benefits of machine learning is that you bring in all kinds of other data that doesn't necessarily have to have been in your equations of motion to do your predictions or your downscaling. But when we do that, we need to be very sensitive to the nature of that data and any potential ethical quandaries along the way that could happen with using it. But also, I think, provides an opportunity to potentially use our weather and climate data in ways that we haven't been able to before. So I think constant communication and engagement with our diverse community will help lead the way, I think.
Yeah, and one way that we're kind of looking at it on the just the satellite operations front, we're mainly just trying to make sure everybody, regardless of who they are, just has access to this data as quickly as possible. So we're trying to use AI in a way where we can basically alert the operators and the engineers of these systems to ensure that the uptime is kept at as high of a level as possible throughout the time, because the people who tend to get hurt the most whenever we have one of these data outages are unfortunately the people who are most vulnerable to this sort of thing.
Thank you. Would anybody else from the speakers like to comment? Okay. Isaac, you're highlighted. I'm not sure whether that means. Okay. Well, I think the session is drawing to an end now. So the only thing that remains for me to do is to thank all of our speakers. It's such a shame we're not there in person, but if you were, the crowd would be going wild. Hurrah, well done. To thank the delegates for all attending. To thank the organising committee and for Chris for helping me through navigate this first session. I'd like to wish you all well for a really fruitful conference this week. And can I please encourage everybody to think about your questions for the speakers? They've developed these amazing talks that we've been so lucky to see. Think about what you want to ask them and get it in the Slack channel. The Slack channel is our way to continue this conversation beyond the end of this session. Other than that, I'd like to thank everybody again and good luck. I look forward to seeing you at the next session.